Now that we have discussed what intermolecular forces are and the ones that we're going to evaluate, now we can start applying that to physical properties. And so we're going to evaluate physical properties, some of which you're probably already familiar with, like boiling point, but through this lens of how do intermolecular forces affect that physical property. So let's start with something that you probably are already intuitively familiar with, boiling point and melting point. So boiling point is when a substance goes from a liquid to a gas and it starts boiling. Like when you're making pasta at home and you put a pot of water on the stove and you start to see the bubbles, boiling point. So that's just the temperature where that occurs. Then we have melting point, which is that temperature at which a solid will become a liquid. So we can predict physical properties, especially in comparison to another compound, and figure out relatively which one will have a higher or lower boiling or melting point by comparing the strengths of their intermolecular forces. And so we see that boiling point and melting point, that temperature at which something goes through those phase transitions, will increase. So they'll occur at a higher temperature when intermolecular forces are stronger. So we can compare in this slide. We've got a few examples. I'm gonna highlight that first. We have three molecules that have almost the same chemical formula. The last one has overall negative charge. We've removed a hydrogen, so its chemical formula is slightly different. But we have different arrangements of these two. And so in our top one, we have an ether, then an alcohol, and then we have our ion at the bottom, our polyatomic ion. And look at the trend of our boiling points. So they're increasing as we go down here. And if we look at these and evaluate them, we can see that the intermolecular strengths increase as we go down this row. So in our first one, we only have London dispersion forces and a small dipole-dipole moment. That ether will create a small dipole moment, but it won't be very large. Then in our second one, we have London dispersion forces, we have a dipole-dipole moment, and we have hydrogen bonding interactions because we have this oxygen and hydrogen bond that'll interact with the lone pair on another oxygen of another molecule, which is, a dipole-dipole interaction, but stronger. And then lastly, because we have this charge right here, because we're a polyatomic ion, and it looks exactly like the one above, we have London dispersion forces. There's a dipole moment as well because we have that electronegativity difference between the carbon and the oxygen that's not canceled out by anything. We have our ion dipole. We don't have hydrogen bonding though, because we lost that oxygen hydrogen bond. It doesn't exist. We only have carbon hydrogen bonds. Like that oxygen with a negative charge could definitely hydrogen bond to another hydrogen attached to an oxygen, nitrogen, or fluorine. But without it here, if this is a pure sample, then we don't have hydrogen bonding. But ion dipole interactions are much stronger than hydrogen bonding interactions. So we can say that this one at the bottom has the strongest intermolecular forces, and we see it has the highest boiling point as well. Now, I'd like to note that in this comparison, we are looking at the same chemical formula for all three of these. The second that I start comparing molecules that also have larger or smaller overall sizes, like more molar mass or less molar mass, then that'll also have an impact on the boiling point as well. And then I'll be kind of juggling a couple different variables if I'm trying to compare a molecule that is small with, let's say, a molar mass of like 20 grams per mole with something larger that's more like, lots more atoms and something like 78 grams per mole. That mass difference would also have an impact on our boiling point. But this was a fairly direct comparison. Now, another physical property that's influenced by intermolecular forces is solubility. And we think of solubility, but with this little rule. Oh, sorry. Solubility we usually characterize as like dissolves like. And what we're referring to by the like dissolves like, that like and like, is when intermolecular forces are similar between two compounds, then it's likely that they will dissolve each other. They'll be miscible. So that miscible word right here just means will can dissolve in one another or is soluble. And so if we have something like hexane, which is nonpolar, it's just carbon and hydrogen atoms bonded together, then we're going to have intermolecular forces that are just London dispersion forces because it's nonpolar. Now, if we think about combining that with water, which is polar, it has London dispersion forces, dipole forces, and hydrogen bonding forces between each of the molecules that are interacting. And so, because the intermolecular forces of the water are so much stronger than the hexane, they won't be very similar at all. So we see these two compounds just don't mix. They're not miscible. They are not soluble in one another. And we will spend a lot of time talking about the impact on solubility from intermolecular forces and look at it in a lot more detail in the next series of lectures for chapter 11. But right now we can note that one of the ways that intermolecular forces plays out in physical properties and behavior is in the solubility of a compound. Next, we're going to talk about cohesive and adhesive forces. And so as we talk about how these are influenced by intermolecular forces and then the physical properties they affect, let's first define them. So adhesive forces right here are the attractive intermolecular forces that exist between different molecules. So that different one's important. So when you have two things interacting, so in the previous slide, it'd be the water and the hexane interacting. Here, I have a picture of water and a spider web interacting with one another. So the spider web silk is a different compound than the water in the rain droplet or dew droplet. And so that interaction between the water and the other compound would be the adhesive force, which is the intermolecular forces between these. Then cohesive forces are the attractive intermolecular forces that happen between the same molecule. So it's when a compound is existing in a surroundings or in a system that it's just going to be how the like molecules that are near each other will interact compared to some outside molecules or space. So now we're going to compare these as we talk about things like surface tension. So surface tension is a property that is going to result from a liquid's tendency to minimize its surface area. And we're going to, in the next slide, talk about why that's happening. But my favorite example of this are water bugs or water skaters, or I feel like my kids have a lot of different names for them, the little bugs that walk on water. And it's utilizing surface tension of water to enable the bug to distribute its mass out and be able to stay on the surface of the water. So we see that the layer of molecules that are on the surface of a liquid behave differently than the interior ones. And it's because they are interacting with fewer molecules on the surface than they would be in the kind of core of the liquid. And so there'll be different cohesive forces for those surface molecules than the ones that are actually inside the interior. So the stronger the intermolecular attractive forces are, we see that the higher the surface tension is. Let's highlight that. We do also see, though, if you raise the general temperature of the liquid, we see its surface tension decrease as those molecules have more kinetic energy. And so looking at this, let's compare a surface molecule and here's a surface molecule and something that is in the interior. So when I look at these, I can see that my my surface one is going to only be able to interact with other molecules around it on part of it, right? So it's in this case, it's only interacting with 4 other molecules. Whereas something on the interior is going to be completely surrounded because it's not on the surface by other molecules or atoms in the liquid. And so the one in the interior has more intermolecular forces between it and other molecules. So it has more of those IMF interactions. Now remember, intermolecular force interactions are attractive forces overall. And so these attractions, they help stabilize or lower the energy of, or make overall more favorable the interior molecule in this case, because it has more of these attractive forces compared to something on the surface that has less. And so because this one has less on the surface, we tried to minimize, or not we, but a liquid will minimize the surface molecules in order to maximize having molecules that have more interactions. So the stronger those intermolecular forces are, the more driving force there is to have all of the molecules that you can in the interior rather than the exterior. And so a water sample will resist spreading. So water particles or a liquid's particles will minimize the number of particles that are on the surface because it's trying to maximize the number of particles that have more intermolecular force attractions because it's so stabilizing. And so because of that, there's this drive to keep as few molecules on that surface as possible. So when something steps on the surface of the liquid, like the bug, there is a resistance to the liquid spreading, because if it spreads, if it like takes the bug down or like it goes into it, then we're going to have an increase in the surface area on the outside of the water, right? And that increase in surface area will take energy because it means we're going to have to break these intermolecular forces of some of the interior water molecules or liquid molecules and make them be surface molecules with fewer interactions. That's going to require energy to do it. And so the harder that is, the more intermolecular forces that have to break to spread that water out and increase the surface area at the surface, the higher the surface tension will be. So we see that water has a pretty high surface tension. It's like 72 millijoules per meter squared, compared to something like hexane, which is just non-polar and just has limited dispersion forces. It's like 28 millijoules per meter squared. So we see this direct connection between the surface tension of something and the number of intermolecular forces it has. All right, let's look at one more physical property in this video, viscosity. So viscosity is the resistance of a liquid to flow, right? So in my mind, I always think of honey. It's just like my go-to. Honey is this viscous liquid that I can think of regularly and with fond, happy memories. So this resistance to a flow can be measured in different units. We have a poise, which is like 1 gram per centimeter times second. So it's looking at the mass traveling over a distance for time, or a centipose. And we're not going to do any calculations with viscosity, but just for reference, water would be 1 centipose, not 100% sure, at room temperature. And what we see is that larger intermolecular force attractions are going to lead to higher viscosity for the same reason that we saw that the higher intermolecular forces leads to a higher surface tension, right? So when something flows, it's spreading out. And so it's increasing the number of surface molecules versus interior molecules. And we have then the cohesive forces of the sample are trying to hold the liquid together and minimize that surface tension. And then we have this comparison to then adhesive forces where that compound's going to interact with something else around it that might help it pull. But for this one, the cohesive forces are going to have that higher influence or stronger influence on the actual properties that we observe. And so as those intermolecular forces strengthen, we see it's harder and harder and harder to, or takes more energy to break those intermolecular forces that are required to increase the surface area of the liquid. We also see, similar to surface tension, that if we raise the temperature of a liquid, will reduce its viscosity. We're inputting kinetic energy into, or heat into the system. And so these particles are going to have more kinetic energy, more ability to move. And so we see that viscosity decrease as temperature increases. So if we were going to do a comparison of viscosity or surface tension between different types of molecules, we would assess their different intermolecular forces and compare those and say which one has more, which one's stronger. But we would also need to make sure that we were comparing these samples at the exact same temperature, because temperature changes would increase our observations or change our observations about surface tension or our observations about viscosity.